this video we will be looking at some details of the linear regression. We had seen a simple plot obtained through MATLAB for a linear fit, a quadratic fit and a cubic fit. The last video we will look at some details of how to do this. Please pay attention to the process that is being shown here, because this is essentially the process that we will be repeating for almost all of deep learning, okay. Especially for the deep learning module. As I said, the paradigm is set by what we do for a simple linear fit, and we will just continue that for quadratic, cubic and then neural networks etc., and even for classification problems. So, here is the example that we saw last time. Last time we looked at temperature versus coefficient of thermal expansion, and we had all this data on the x axis, let us call this x, and we have all this data on the y axis, let us call this y. Okay, so, this y, as I said earlier, is called the ground truth. This is basically the experimental truth or the reality that is available to us. What we would like to know is what happens in between. That is the classic regression problem. We would like a fit for this data, and we saw 3 different kinds of fit last time. One of the fits was a linear fit. Okay, you see that actually this line, which we can call y hat, which is a function of x called the hypothesized function of x. Okay. In fact, we had hypothesized this to w0 plus w1x. Okay. So, this is y hat versus this is y. Okay. For the same x, you have the real prediction and you also have the hypothesized prediction. Okay. So, we saw that there was a difference between the two, but nonetheless overall trend is captured by the hypothesis. Okay. So, that was one of the things that we saw last time. We also saw that if you put a quadratic fit, okay, so in this case let us say this is y hat. Okay. So, quadratic shown in red here, that is a little bit better than linear, in fact it is reasonably better than linear, and cubic, which is mildly better than quadratic, almost indistinguishable. So, we had all these different fits that we had for the same set of data. Why do all these fits differ? Because our h of x, okay, our model for what y is like, which we call y hat, is actually different for each of these cases. So, we had linear, quadratic, cubic. So, for example, for quadratic we had w1x plus w2x square, so on and so forth. Okay. So, what we will see in the next videos is how do you actually come up with the coefficients. Okay. So, I just use some inbuilt MATLAB function. Now, we are going to do it from scratch in the coming videos. Okay. So, let us look at this general problem. Just like the previous problem, you have some x and you have some y. Okay. You have some scalar x and you have some scalar y, and each of these data points is, we can label it as data point 1, data point 2, so on and so forth, and let us say there are m such data points. So, you have a single input like the temperature and a single output like the thermal coefficient. Okay. So, let us say we take this data pair xi, yi and we call it the ith example. Okay. Why example? Because later on we will see for images I will say this is an example of a cat, okay. This is an example of a dog. So, each image is also called an example. This is simply machine learning terminology, you can call it data point. Okay. So, ith example simply means ith data point. So, in this figure let us say I think there are approximately 51 points. So, you could start with x1 y1 and go up till something like x51 y51, okay, something of that sort. So, you have all these points, and what we would like to see is which hypothesis function fits these the best. Remember this terminology, we will be using a lot of letters, and within our course m simply means the number of data points or number of examples that you have. Please remember this. Okay. Now, let us look at how you do the fit. Here the input output is actually the given data and y hat is our model, okay, above and beyond the data that is given. Okay. So, you have x1 y1, but you are guessing what y hat should be for the given x. Remember, like the example we gave, x was temperature, y was the thermal expansion coefficient. This is the actual and you will guess something else. Okay. We are going to introduce our very first for this course model hypothesis. This is a simple, very trivial linear model, but it is enormously powerful, okay, as you will shortly see in the next couple of videos. Okay. Now, there is only one question. We have already fixed the form of the function, and as I said in the previous video, we still have the parameters. The parameters are unknown. What W0 and W1 should I fit? Now, obviously, for different choices of W0, W1, even in each case, even though in each case your hypothesis will look like a line, it is going to look like a different line depending on what W0 and W1 you fixed. Okay. So, suppose somebody randomly gave some values of W0 and W1, here is the original data, here is your hypothesis, this is the data, this is your hypothesis or the model based on the model parameters, some model parameters that we chose. Now, it does not look like a very good fit, okay. Intuitively it does not look like a good fit. So, somebody else, another person gives a slightly different model and this looks slightly better than this, okay. Again we have an intuitive notion of what is better, we will formalize this in this very slide, okay. So, this looks better than this because all that has changed here is W0 and W1. Remember, all three are still lines. Now, this one looks really good, this one looks much better than this, also much better than this. So, the question is there any way in which we can formalize or quantify? Remember this word, in machine learning we are always looking at quantitative things, we are looking at numbers, okay. So, the machines only recognize numbers. So, is there any way in which we can quantify why this is better than this or this? And the idea goes back to an old idea which we have, which is a cost function. Okay. So, what is a cost function for this? It is simply one single number that will tell you how good the fit is. Okay. So, how is it going to say that? Now, for each point, let us say I take this x, there was a y, there was also a y hat. So, there is a difference between the two. What do? I take the difference between the two, square them and then add it. Okay. So, this let us say this was y1 and this was y hat 1, this is y10 and this is y hat 10. Okay. So, for the same x you find out the y and the corresponding y hat, square it, add all of them. How many examples do you have? You have I equal to 1 to m. So, you have 51 such examples. We sum up all the squares, this is basically sum of the square of the errors, and you say whichever line or whichever choice of W0 and W1 minimizes this total error, I am happy with that. Notice that no line is going to fit all of these perfectly, you cannot drive this j to 0 because no line will fit all points, but overall overall it will sort of kind of split the data so that you do not go too far away from the line. Okay. So, this is how we achieve our optimal W. Okay. So, we say that the optimal W, so you can now notice it has now become an optimization problem. An optimal W is the one which minimizes this net cost function. Now, a couple of things, I have put by m here, this is arbitrary, even if you remove this 1 by 2 m the minimum will be the same, but this m is often used because you would like mean of squared error for several reasons. One is of course to avoid some kind of overflow errors, you sometimes just take a mean. Another thing is this 2 is also arbitrary, but it is put there just so that when you differentiate this function, the 2 and this 2 will cancel out. Okay. This fit is called the least squares fit. Okay. So, the W's that we get at the end of them end of the process will be called the least square coefficients, okay. And this cost function is sometimes called the least mean square cost function or the mean square cost function, sometimes called LMS. Okay. Okay. Now that we have reduced our fitting problem to an optimization problem, can we use gradient descent, which we discussed in the previous week. So, gradient descent we used as a general one box algorithm in order to find out minima, and it turns out we can use gradient descent. How do we do it? Very simple idea again. You start with an x, some data point for a temperature that is given, for example, guess some w, this w is remember true for all x, run it through the hypothesis, our y hat was the linear function w naught plus w1 x, the ground truth is already available, we just got our hypothesis because we guessed the w. Now, there is going to be a gap between y and y hat, square it, sum it. that is going to give you the net cost of the coefficients that you have chosen. Okay. Remember, this net cost is because we have chosen some W 0 and W 1. Then find out gradient and improve your W by using gradient descent. So, let us see this again. You have m data points, let us say 51 just as an example. Now, for each of these data points you can get a corresponding y hat provided I give you some guess for W 0 and W 1. Okay. You have the corresponding output, then you calculate the net cost function. Okay. So, which is y minus, remember what this is y hat I. So, y I minus y hat I squared will give me the net cost function, and then you improve W by using gradient descent. When do we stop? You keep on doing this, you have some stopping criteria. I gave you 3 different types of stopping criteria and we will see at least 2 of them in an example shortly. Okay. So, if you use your stopping criteria, it will stop. The final results that you obtain for your W are actually your regression coefficients. So, you can carry out this whole process, but theoretically you have only one small catch. How do you calculate this gradient of j with respect to W? Okay. So, let us see that. So, our j, as we saw on the last slide, is summation of y minus y hat square. Y hat was W 0 plus W 1 x. So, you get y minus W naught minus W 1 x square, and we want gradient of W. We want gradient of j with respect to W. Notice that W is a vector. So, W is basically in our case W naught W 1. I will avoid the transposes. Similarly, gradient of j is gradient of j with respect to W naught, which is nothing but del j del W naught and del j del W 1. Okay. So, I am just writing out this both the components of this vector equation. W naught is W naught minus alpha del j del W naught, W 1 is W 1 minus alpha del j del W 1. Okay. Now, we want these 2 expressions. Okay. I will show you that they can be written in a compact form like this. Okay. Please do not pay too much attention to this before the derivation, but the derivation is extremely straightforward actually. Okay. So, let us take a simple case. Let us take the case that m is equal to 2. Okay. I will just do the derivation for that and you can see that it easily extends to any type, any number of n. Okay. So, let us give a proof of this statement. So, suppose I want del j del W naught, okay, for the case where m is equal to 2. I will keep the 1 by 2 m here. Now, what terms will I have? I will have y 1 minus W naught W 1 x 1 square plus y 2 minus W naught minus W 1 x 2 square. These are the only 2 terms that exist, and now I have to take del by del W naught of this. Okay. Since it is a partial with respect to W naught, only this terms are actually dependent on W naught. Okay. So, how do we do this? 1 by 2 m, take this term, this is the same as 2 times y 1 minus W naught minus W 1 x 1, okay, multiplied by derivative of this term with respect to W naught, which is minus 1, plus 2 times y 2 minus W naught minus W 1 x 2. So, the 2's cancel out, which is why we had 2 in the definition in the first place. So, you are going to get 1 by m, I will take the minus out, you will see y 1 minus this is nothing but our hypothesis function y hat 1 plus y 2 minus y hat 2. Okay. So, this means that del j del W naught is minus 1 by m sigma of y I minus y hat I, I equal to 1 to m. You can see easily that this will continue for any m. Okay. Now, what is this term? This is nothing but the error. So, what it tells us is that the first component of the gradient is simply the sum or the mean, the error, mean error. Okay. It is not mean square error, it is simply mean error. Okay. Also notice you can write y hat equal to w naught plus w 1 x as w naught x bar 0 plus w 1 x bar 1, and usually we will call this x bar 0 as x naught. Okay. You will see the power of this notation later. Because of this, when I say del j del w naught, I am going to say x naught I, where x naught is nothing but 1. Okay. That just lets me write this whole expression compactly. Okay. Let us look at del j del w 1. I will derive this in a slightly different fashion, just to give you another tool near tool set. 1 by 2 m del by del w naught of del by del w 1 of sigma I equal to 1 to m of y I minus y hat I square. Okay. Let us deal with this in this form itself and see if we can do some algebra quickly. Okay. So, this is equal to 1 over 2 m sigma I equal to 1 to m 2 times y I minus y hat I multiplied by minus del y hat I by del w 1. So, what did I do here? Instead of expanding y hat fully into w naught and plus w 1 x, which I did last time, I am just differentiating this directly. So, derivative of this term with respect to w 1 is nothing but 2 times this term multiplied by derivative of this term, simple chain rule. Okay. So, I am just going to use this here. So, the 2 and 2 cancel out once again, we are going to have minus 1 over m sigma I equal to 1 to m y I minus y hat I multiplied by del y hat I by del w 1. Now, what is del y hat I by del w 1? Remember, y hat I is w naught plus w 1 x I, okay, which means del y hat I by del w 1 is simply equal to x I. So, this gives us minus 1 I equal to 1 to m y I minus y hat I times x I. Okay. So, let us go back to this term here. Okay. So, you see this j here and j here. What does this denote? Del j del w 1 is equal to y I, correct, minus y hat I, correct, times x I, this is also correct, except I will have x 1 I here, x 1 is nothing but x power 1, which is equal to x. Okay. That is simply the notation. Similarly, if I take del j del w naught, I will get y I, which is correct, minus y hat I, which is also correct, multiplied by x naught I is simply 1. Okay. So, it is just compact notation. If you are not comfortable with this, that is fine. You can simply write both these terms individually and say that del j del w naught is minus 1 by m times sigma of y I minus y hat I. Similarly, del j del w 1 is minus 1 over m sigma of y minus y hat multiplied by x. Okay. So, what are the steps of the linear regression procedure? We first decide on our learning rate. Remember, learning rate is required for gradient descent, and we also have to decide on what our stopping criterion is. We will make an initial guess for the weight vector. Okay. Then systematically you will calculate the next iteration. Okay. Now that you have one weight vector, you have one guess for W naught and W 1, you will make another guess. How do you guess this? By using the formula that we just derived. Okay. And once you update your W, you calculate your stopping criteria. If this works out, you stop. If it is not satisfied, you go back here, you calculate once more, you keep on stepping through the gradients. Okay. So, in the next video we will actually see a code to implement this, and hopefully all of these things will come together very nicely. This is one of the reasons why we insist on doing the code, because in theory you might understand something, it is only when you actually see it practically implemented into a code that things become clearer. We will be using, as we had declared earlier, we will be using an example through a MATLAB code. All of you are welcome to use whatever programming language that you would like to see, but MATLAB is usually the easiest to explain things as well as to visualize things nicely. So, we will see that in the next video. Thank you.